another, to the ratios of the speeds of the light or the ratios of the wavelengths or the ratio of the sines of the angles. We're going to be doing the lab that I talked about tomorrow because it requires me to set it up the night before, and I didn't want to set it up Friday and then have it sit for 3 days because it involves something that would deteriorate over time. Okay, so it has to be set up within about 24 hours. What is the index of refraction? The index of refraction of light in a particular substance is merely a measure of how dense the substance is optically. What that means is that if n has a value of, for example, 5, which I don't know that there's a substance in the universe with an index of refraction of 5, but if there were, the speed of light in that substance would be 1/5 of what it would be in air or a vacuum. That means when you start talking about the index of refraction of light in air, and I don't like this subscript, this is what you always see on exams, or the index of refraction of light in a vacuum. I don't like this notation either because it's not an index of refraction of air. It's an index of refraction of light in air. But that's the notation we use. In a vacuum, this is equal to 1.0 exactly by definition. It's the least dense optical material that light can travel through, which means it travels as fast as it possibly can, which is the speed of light in a vacuum. And if you looked it up online, you wouldn't see 3.00 times 10 to the 8. You would see 2.99 something, something, something times 10 to the 8. The index of refraction of light in air is so close to the index of refraction of light in a vacuum that we use 1.00 for air. What this number actually is, and I don't know, you might remember this before I do, I think it was 1.003. And there might have been some other decimals after that. So since everything on your formula sheet in terms of constants are rounded to 3 significant figures, that's why we see 1.00 in our calculations. You know, it's like Coulomb's constant. If you look up Coulomb's constant, it's 8.99 times 10 to the 9. I don't know whether that's rounded up or rounded down. I've never actually looked, so maybe we'll... It's I don't know if you can read that or not, 8.9875517. I mean, they do all these experiments to try to determine these things. Even that is rounded, okay? When you use Snell's law, it's important for you to remember to be in degrees, obviously, because there's some trigonometric properties to this law. And don't forget that it's n2 over n1, and everything else is 1 over 2. It's intentionally, backwards is the wrong word, it's intentionally opposite because as n gets bigger, everything else gets smaller. So take a look at your work, please. Does anybody have any questions you would like me to go over here? Sienna? 9? So a ray of light strikes a surface of water at an angle of 60 degrees from the water's surface. What is the angle of refraction? So at first glance, this looks like a straightforward n2 over n1 equals sine of theta 1 over sine of theta 2. One thing I didn't say in my review is of refraction is theta 1 is the angle of incidence and theta 2 is the angle of refraction. And 1 is always the subscript that describes where it starts. So if it says it strikes the surface of water, it never really says from air, but that's implied. It's going from air to water, which means that in this formula, N2 will be the 1.33, N1 will be the 1.00. It goes from, which is where it starts in 1, air, so N1 is the air, and it enters into afterwards the second medium, which is water. Now we're asked to find the angle of refraction, so I'm just going to leave the bottom as sine of theta 2. But on the top, we're going to have to put sine of 30 degrees, not 60. And the reason for this is it says it strikes the surface of the water at an angle of 60 degrees to the surface. And that makes this 60 degrees. But Snell's law only works when you use theta, whether it's 1 or 2, between the ray of light and the normal line. So we would have to say that the normal line is perpendicular, which means 90 degrees away from the boundary or interface or water surface. And that's where I'm getting the 30 degrees from. Are you okay with that now? Okay. In calculus, if you take calculus with me next semester, we do an exercise where we prove Snell's law. And it turns out that light follows that path because it's the path that gets the light to a destination as quick as possible, which is kind of strange. If you start off and you say, well, determine the path of light mathematically from this point in the air to this point in the water so that the light travels in the least amount of time, turns out you get that path. Just a side note, curiosity. Other questions? Go ahead, Zebi. 11? Monochromatic light. Well, let's break down what that word means. Monochromatic simply means one very specific wavelength or color. The word itself, mono, means one, chromatic means color. But when we talk about monochromatic light, we mean it's not just red. It's this exact color of red. So it's just a way of saying a specific wavelength. The wavelength is 622 nanometers. I really dislike this mixing up of scientific notation with metric prefixes. On the one hand, this 6.22 times 10 to the 2, first of all, I don't know why we can't just write that as 622. And we can. But I'm saying I see this on exams all the time, diploma exams, where they go 6.22 times 10 to the 2. Sorry for screeching to a halt here, but I don't think I mentioned this officially in this class. Your diploma exam, all of the diploma exams this year are worth only 10%. So I'm sure you know that, but if you don't, now you do. So that really does take the pressure off of you as students. It somewhat takes the pressure off of me as a teacher. I would still like you to do as well on the exam as the mark I give you, but if you don't, it's not the end of the world. And then it says nanometers. So what this actually means, and I don't think that this is the sticking point in this question, but what this actually means is this many meters when you put it all together. Okay. It enters a lucite material. Again, we presume it's from air, and we want to know the frequency of the light in the lucite. So I'm going to go through some calculations here. And what I'm going to be doing is using the universal wave equation and saying that the speed of light in the lucite would have to be equal to the frequency of the light in the lucite multiplied by the wavelength of the light in the lucite. I want to really make sure you understand that you can't take the universal wave equation and apply it to light if you're going to put the speed of the light in one medium and the wavelength in a different medium. We've got to be consistent. So we need to know, I guess, the speed in the lucite. So we can use N2 over N1 equals V1 over V2. And it's going from air into lucite. So V1 is the speed of light in air. And then we can find V2. And I'm going to find V2, and I'm going to store it on my calculator because I want to carry all the decimals to make a point. So I'm simply going to take the speed of light in air and divide by 1.51. So this is, wow, really slow, like only 2/3 the speed of light in air. I'm going to store that as A. I'll just remember the speed of the light in the lucite is A. Now, if I want to find the wavelength of the light in the lucite, because this is my strategy here. This is my strategy. So I can even put in this number, 1.9 whatever times 10 to the 8 meters per second. I'm trying to find the frequency in the lucite. So where I'm at in my logic now is, well, what do I put for the wavelength of the lucite? And it almost looks like I've drawn a fraction there. I didn't mean to imply that. I was just underlining it. So we need to find the speed in the lucite. Okay. Well, we can use n2 over n1 equals lambda 1 over lambda 2. So I can write 1.51 over 1.00 equals 6.22 times 10 to the negative 7. I don't know if or how many of you remember me saying this, but when we talk about nanometers, often it's hundreds of nanometers, because visible light is hundreds of nanometers. And when you convert hundreds of nanometers to standard scientific notation, it boils down to something point something times 10 to the negative 7. And this is meters, and it is over lambda 2. I want to stop for a second here because I could have just put 622 nanometers here. I could use nanometers in Snell's law. The only problem is looking ahead, this wavelength needs to be in meters for the universal wave equation to work. Okay. So I'm going to calculate the wavelength using Snell's law by taking 6.22 times 10 to the negative 7 dividing by 1.51. And this seems like an awfully long way to go to get an answer to the question, but bear with me. So this is the wavelength, 4.12 times 10 to the negative 7. And I'm going to take the speed of the light in the lucite divided by this. I've carried all my decimals. There's the speed of light in lucite divided by the wavelength. Gives me this number. So this is the answer to the question. Okay? But I told you that the universal wave equation could be used as long as you use consistent media, like air, lucite, etc. And if you remember, during refraction, frequency doesn't change because the frequency is determined by the source that starts the oscillation. If the oscillation just goes into a different medium, that different medium is still going to oscillate the same way because it's connected physically. It's an electromagnetic wave, so it's not connected physically, but the analogy still works. It's still connected physically in some way or electrically in some way to the original oscillation. So this means that if you were to take 3 times 10 to the 8 and set it equal to the frequency in air times 6.22 times 10 to the negative 7, you should get the same thing. Some of you will see why you get the same thing, because the mathematical operation we performed on V1 to get V2, dividing it by 1.51, is the same as the operation we performed on lambda 1 to get lambda 2. So these two numbers up here are simply these two numbers down here divided by the same number, 1.51. So when we take these and divide them, you're going to get the same ratio, which is the frequency. Again, not just, well, it's close. You get the same thing. There's a classic question that they put on a diploma exam a long time ago, like maybe 12 years ago. And it was really surprising that they had the guts to do this. They told you that light of a particular wavelength went from air to water to glass to plexiglass, back to water, and then to something else. Like it was a series of 7 or 8 different layers that it went through. And it said, what's the frequency in the final medium? Well, just find the frequency in air. Maybe that was the point of the question. It was so impossible to do unless you realized you just find the frequency in air. Anyway, Zebby, are you okay with that? Okay, good. Any other questions? All right, so we are going to be looking today at something called total internal reflection. And total internal reflection refers to the fact that when light is in a particular medium, sometimes it cannot refract out. Okay? And we're going to be looking at the conditions necessary for total internal reflection, which is, just as important, maybe not just as important, but it's important to know when total internal reflection might happen. Okay, so what does that mean? There are certain circumstances that we will look at and we will go, total internal reflection will never happen in these circumstances. And there is another set of circumstances where we look at it and we say, total internal reflection can happen. And then we can dig down a little deeper and say, if it can happen, under what more specific situation will it happen? It's really confusing. And then we're going to be doing calculations with it. So we're going to start off by looking at light traveling from a block of glass into air. Let's forget for a second how the light got in the block of glass first. Let's not forget about it. It probably went from air into glass, but we're interested in what happens when the light leaves the glass and goes into air. And what is important here, well, we can draw a block of glass. I don't care if you draw a rectangle. You can just draw a line. It doesn't matter. What is important is we understand which way the light will refract. So the light is in the glass. Again, how did it get there? Well, we shone light from air and it went into the glass, but we don't care about that. Now, there's the beam of light in the glass. So again, there's some laser down here that got the light in there, but we don't care about that. We're interested in glass to air. And we should know which way this will refract. We should be able to look at the index of refraction of the glass, which is 1.65, and know the index of refraction of air, and we should know whether it's going to refract towards the normal or away from the normal. And since it is traveling into a less dense medium, I don't know that you need to write all this, but since N2 is smaller than N1, so it's going from 1.65 to 1.00, then it will refract away from the normal. It will also speed up, and the wavelength will increase. I'll give you a second to write that down. And I can let everybody know that this is the precise, give me one of those afternoons, eh? That this is the precise set of circumstances needed if total internal reflection can happen. I'm not saying if that's the case, it will happen. I'm saying unless that's the case, it can't. So when we sketch this, we know, because air is less dense, it refracts away from the normal. Okay, so the diagram looks like that. So we looked at this last time. Last time we were more interested with light going from the air into the water, but if I do this, you can see that the light is going, it starts down here where the laser is. This is the laser, I'm covering it up. The light starts in the little laser diode thingamajigger, and the light hits that boundary at the normal line and it refracts away from the normal line. So the angle, I don't know that you need to actually put the relationship here, but the angle of incidence is this angle down at the bottom, and the angle of refraction is the angle at the top. Good? Yeah. Is it buzzing again? Okay, I'm sorry. I thought somebody told a good joke back there or something, but I knew that something was up. Is it off now? Okay. You know, you can make an observation here that theta 2 is bigger than theta 1, which is key in understanding that total internal reflection might happen. So we'll talk more in detail about this, but if total internal reflection can happen, the light has to be bending away from the normal. If it doesn't, then it will never happen. All right, so find the angle of refraction for each of the following angles of incidence. I don't know that I mentioned this on Thursday or not, but be very careful not to confuse index of refraction with angle of refraction. They're different things. So if you look up here, here's Snell's law as it applies to the problem we're working on here. Sine of theta 1 over sine of theta 2 equals n2 over n1. Now, glass is the first index of refraction. If I cross multiply this, and by the way, this statement right here is how Snell's law is written in pretty much every university text. I don't know why we write it in high school as n2 over n1 equals v1 over v2. But glass is the first medium. Clearly, what we're talking about with this demonstration is it's water to air, right? But water is more dense than air, just like glass is more dense than air. So the physical appearance of this beam of light that we're actually looking at in the room is the same as what you've drawn. N1 is 1.65, N2 is 1.00. So what does this mean? It means that we can calculate sine of theta 2. I don't even need the 1, do I? You can take 1.65 times sine of 32 degrees and then go inverse sine. And I would like everybody to find these 4 angles of refraction for those 4 angles of incidence. This is that trigonometric, I don't know why I got that twice, doesn't matter. This is that trigonometric relationship that's hard for us to wrap our heads around. Look how quickly the angle increases. It goes from 61 to 67, and then you go up by 2 degrees for the angle of incidence. And I mean, it climbs. It climbs to, you know, not almost 80 degrees, but around 76 degrees. And then what happens when you try it with 38 degrees? I hope you're at this stage. You get an error. I don't know what your calculator says. Does it say domain error maybe? It does say domain error. That's got nothing, don't overthink that in terms of math. It just means that you can't do it. Now, why can't it do it? So first of all, a lesson to be learned is if you get an error in calculating an angle of refraction, what it's telling you is refraction doesn't occur. It's telling you total internal reflection occurs. And I can show you what that looks like here. Can everybody see that there is some light refracting here? It's getting into the air. But if I increase this angle of incidence enough, I'm guessing there's no refraction there. You're looking at 100% reflection inside of the medium that it's in. Total internal reflection. So when you're going from a more dense to a less dense medium, if that angle of incidence is too big, you get reflection. So when I say no refraction, I mean 100% reflection. But why? Why are you unable to calculate an angle? I think this is important. You are unable to calculate the angle. Well, I might as well do it on my calculator. We're going 1.65. 1.65 sine of theta 1, which is 32 degrees. And then I'm going inverse sine. So look at that number. I'm going to take the inverse sine of 0.87. What does that mean? It means I'm trying to find an angle whose sine is 0.87. And I don't want to turn this into a unit circle thing, but the sine on the unit circle is the y-coordinate on the unit circle. For you non-unit circle people, for you non-Math 30 people, -1, sine is opposite over hypotenuse. So what you're doing here is you're saying if the opposite side is 87% as long as the hypotenuse, what's that angle? It makes sense. If I do 1.65 sine 34, I get this. And I have to take the inverse sine of that, right? I didn't do that in the last example, but I could. Inverse sine of that answer. So it's 67 degrees. But again, that number 0.922 is the ratio of the opposite to the hypotenuse side on a triangle. Or it's the y-coordinate on the unit circle. And then you go, well, inverse sine of, whoops, I got to do this first. Then you take 1.65 sine 36 and you go inverse sine of the answer, and you get that. You do the same thing with 38 degrees, and here's where the problem arises. You may not have even looked at that number before you went inverse sine. That number is bigger than 1. So for you trigonometry people in Math 30, that's saying the sine is greater than 1, and it can't be. Sine of theta goes up and down between -1 and 1. For you just regular SOHCAHTOA thinkers, and that includes people in Math 30, this is saying the ratio of the opposite side to the hypotenuse is 1.01 something, which is saying the opposite side is bigger than the hypotenuse. Well, that never happens. The hypotenuse is the longest side in a right angle triangle. So, when you are unable to calculate an angle of refraction, refraction does not occur. Instead, the light will reflect off of the boundary back into the first medium. So, no, I don't need to show that to you. If the angle's big enough, it's just going to reflect, and that's called total internal reflection. Mathematically, this happens if you end up trying to take the inverse sine of a number bigger than 1. Here's the challenge problem I want to just give you a minute to think about. What's the biggest possible angle where total internal reflection will not occur? Like when you look at that chart, 36 degrees, refraction occurs. 38 degrees, it doesn't occur. I want you to find the biggest possible angle that we could still have for an angle of incidence where you would be allowed to go inverse sine. And I'm curious, this is sneaky, if anybody has an answer and it's got lots of decimals, like you didn't just estimate it, was anybody able to get like to the 12th decimal? Farhan, you think you have it?
Wouldn't it be 1 divided by 1.65? Wouldn't it be 0.60606?
Wouldn't what be?
I mean, the angle would be 37.305.
Yeah. So the thinking is this. This thing, this 1.65 sine theta 1, this must be less than or equal to 1, right? That looks wrong. This must be less than or equal to 1. If that thing is not less than or equal to 1, you can't do it. So what's the biggest value that this could take on? 1.65 sine theta 1 being equal to 1. If it's exactly equal to 1, theta 1 will be as big as possible. And I realize that when most people see this problem, you try 37 degrees. Does 37 degrees work? When you go, it does. And then maybe you try 37.5, and it does or it doesn't work, and you try to whittle it down. But when you take this approach, and there's a better way to explain this, you don't have to think this reasoning through every time in Physics 30. I will explain it in a different way. And I will explain to you why it has to be equal to 1, physically, not just mathematically. If you take the inverse sine of that, you get, I'm not going to write the numbers down. You get this number. Now, okay, so I'm going to do this. Okay. So that's the answer to this question. And by the way, that's probably an irrational number. The decimals go forever. Okay. This angle is called the critical angle. Okay. We're not going to answer D right now. I want to talk about the critical angle. It's called the critical angle because if the angle of incidence is less than the critical angle, if that initial angle of incidence is less than the critical angle, refraction happens. But if the angle of incidence is more than the critical angle, the light reflects. Total internal reflection happens. So what if the angle of incidence is equal to the critical angle, which, to be honest, would be like trying to balance an egg on the edge of a sharp knife. I don't know that I could actually move this arm on this laser apparatus so that it's exactly at the critical angle. But if it's less than the critical angle, if the angle of incidence is less, then refraction occurs. By the way, there is some reflection happening here too. We talked about that the other day. Does anybody have an idea of what's going to happen if the angle of incidence is exactly equal to the critical angle? Theoretically, what should happen? Would you want to take a guess? I mean, nobody's going to get hurt if we guess. Ben? Straight on, exactly right. It's going to refract, but not, this is weird, it's going to refract, but not refract into the second medium, because if it did refract, then the angle of incidence would be smaller than the critical angle. And it's going to refract, but it won't refract enough to reflect. And what this means is that theta 2 is 90 degrees. This is a really important thing to remember, that to find a critical angle, the critical angle will be theta 1 as long as theta 2 is 90 degrees. So when theta 2 is 90 degrees and you find theta 1, you are finding the critical angle because it's the angle that results in that balancing the egg on the edge of the knife. And that's actually the answer to D. And I'll bring this up again shortly if you want. It says, how do we find the critical angle? You would start off with n2 over n1 equals sine theta 1 over sine theta 2, but you make theta 1 the critical angle, and you make theta 2 90 degrees. That's what we do. We take Snell's law and we rewrite it as n2 over n1 equals sine of the critical angle equals sine of the critical angle, because sine of 90 degrees is 1. And that's that 1 we were talking about when we go 1 divided by 1.65. I don't want to mess up our work here. This is the answer. We're done with D. But in our example, n2 was 1, n1 was 1.65. Sine of the critical angle was equal to 1 over 1.65. Now, I'm going to erase that because I don't want you thinking it plays a role in what we're doing here. This is a general way for you to find the critical angle. But again, use 90 degrees as theta 2, then what your theta 1 becomes is the critical angle. That's what you're doing when you find a critical angle for total internal reflection. So a couple of quick demonstrations here. This is going to lead into tomorrow's stuff, but if I do it now, we only have a couple of quick examples to do, and if I do this now, it'll lighten the load on tomorrow's lesson. So I have a green laser, and I have a piece of lucite plastic. This is not hollow. Okay, if you try to, poke inside of here, it's like not a hollow thing. But when I shine the green laser in here, you can see it kind of bouncing off down between my hands, right? And the idea is that it will really, was that bright? How about now? I'm just kidding. It reflects a lot of the light. This is total internal reflection. This is a model actually that we use for fiber optic cables. You've heard of fiber optic cables. We'll talk more in detail about them tomorrow, but not all internet connections, but the internet connection I have coming into my house is fiber optic cable. And it's this stuff. It has a different color cladding on it, plastic on it, and it's white, but inside it's glass. It's hard to imagine, but it's glass. If this, it's called cladding, if this protective cover were removed and you took a piece of that inner material and you bent it, it just shatters. But because it's wrapped in something, it is unable to shatter when you bend it. And this is running up across the other side of the room, and it comes out over here. Ow! I'll just put this here, maybe, if that'll. Well, I'll just bend it. There, you can see the end of it. So rather than having electrons move around giving us an internet signal, what happens is it's laser lights. You can see that? I mean, that's pretty cool. And it doesn't matter how long this is. You're getting 100% total internal reflection because of the black material here, that even if any light happens to refract out, it reflects off of the interface. You don't see, when you do this, and I won't show you the bright end, you can see glowing everywhere, right? That means you're losing some light. Some light is not making it all the way around and out this end. 100% of this light is. And this can be tens of thousands of kilometers of length. And the beautiful thing about it for internet speeds is you can send a signal one way through it at the same time as sending a signal the other way. Because light goes through light. More complicated than that, but that's the basic gist of it. We'll talk more about total internal reflection tomorrow in terms of fiber optic cables. How many of you have seen those lamps that have pieces of plastic that glow on the end? That's working on the same principle of total internal reflection. Let's try a couple of examples now. Oh, right, one more thing. I really feel as though I should abandon this question in my lesson. I put this question here to try to reinforce that the light has to travel from one medium into a less dense medium. If you have light traveling from air to water, it will never totally internally reflect. It's got to be from a more dense to a less dense medium. Why is that? Ultimately, it's because when the light, if the light is going to reflect 100% internally at some point, and if you're watching this on a video, I'm showing them this, then it has to begin the journey by refracting away from the normal. I mean, if this were refracting towards the normal, and I can show towards the normal right now, it doesn't matter how big I increase the angle of incidence. If it's refracting towards the normal, it will always refract into the second medium. So I'm really close to abandoning this question in the notes, but the bottom line is the total internal reflection only has a hope of happening if the light is refracting away from the normal. If it refracts towards the normal, forget it. It will never 100% reflect because some of it will always refract. What I would hope that you know is more dense to less dense is needed, or refracting away from the normal is needed. So if you can remember that, and you can remember that when you want to find theta critical, you have to assign 90 degrees as a value to theta 1. Nope. When you want to find theta critical, you have to assign 90 degrees to theta 2. Then you're golden here. What's the critical angle for light in water? So what does this mean? It doesn't mention a second medium. What it would mean is the other medium is air. If it doesn't say, we all understand it means if light were in water, what would be the critical angle going into air? I know you know how to do this, but I'm going to write out Snell's law again. To demonstrate the process where theta 1 becomes the critical angle we are after, and theta 2 becomes 90 degrees. I suspect that many of you would just write sine of the critical angle equals n2 over n1. Because you know as soon as you're going to put 90 degrees in, sine of 90 is 1. Am I right on that assumption? For some of you? Okay. So again, this is 1. This becomes sine of the critical angle equals, well, the two n's are 1 and 1.33. Which is which? Well, it's always more dense to less dense in this context. So N2 is the water, is the air, N1 is the water. So it's inverse sine of 1 over 1.33, which I think is about 47 degrees. If memory serves, and sometimes it doesn't. 48.8 degrees. So now we have to discuss something, because I don't want you to psych yourself out on a diploma exam. So theta 1, or theta critical rather, is 48.8. And let's say you were asked to round to 3 digits, that would be what you would record. No problem, okay? The problem arises, and I wonder if it will work for this one. The problem arises, good, where you get something like this number. This is what we got for the critical angle for light going from glass to air. And you're asked to round to 3 digits. That's what the instructions are. So the answer is 37.3 degrees. And I'm telling you, that's the answer. You put anything else, you're wrong. Because a good student can get psyched out here and go, well, yeah, but this is actually less than the critical angle, isn't it? When you look at the decimals, it's a little bit less. And they go, well, I guess then I have to record 37.4. Don't do that. If you're asked to round it to 3 digits, you round it to 3 digits. You're not trying to figure out which way you should round. You round according to the rules of rounding. G, what is the critical angle for light traveling from diamond to ethanol? I want to point something out to you before we answer this question, that I didn't have to give you the question worded this way. What I could have done is I could have said instead, find the critical angle for a diamond / ethanol interface. I didn't have to tell you it's from diamond to ethanol. Because if I'm saying what's the critical angle, we're talking about total internal reflection. And if we're talking about total internal reflection, it has to be more dense to less dense. So even though you could decipher that piece of information from the way the question is originally worded, you should know that this must be N1 because it's a bigger number than this. So if I just said, is that right? And this is confusing. I always have to stop and think about this. More dense to less dense, that's right. So I didn't have to tell you where the light started. I could have just said the interface is the boundary between diamond and ethanol. So sine of the critical angle, which is theta 1, over sine of 90 degrees, which is theta 2, equals N2 over N1. We're going to get sine of the critical angle equals 1.36 over 2.42. By the way, if you're finding a critical angle, and you go inverse sine to find the critical angle, not an angle of refraction, and you get an error, then you put these in the wrong order. Okay, when you're finding the critical angle. So it's approximately 34.2 degrees. Any questions with that example? Okay, so what's happening here in the next while is today you're working on these problems dealing with refraction and reflection. The first set of problems is pretty much refraction and total internal reflection. The first set of problems is pretty much total internal reflection, but then you start getting to things like this, which is not necessarily a total internal reflection problem. It's geometric optics where you're trying to determine, using refraction and reflection, what's going on.